Hello, welcome to my video on data structures. In this video, we will introduce two new data structures, the queue and the stack. The queue and the stack data structures are derived from the array or the linked list data structure. Like array or linked list, queue and stack both store the data elements as a list, but only a subset of data access and management operations from array or linked list are allowed in queue and stack. Specifically, queue only expects the access of the very first element. It also only allows for data being inserted at the end and deleted from the beginning of the list. For stack, it only expects the access of the very last element, and it only allows for data being inserted and deleted from the end. For queue, because we can only access and delete the very first element, which is first inserted to the queue, we can describe its behavior as first in, first out. On the other hand, for stack, since we can only access and delete the last element, which is the most recently inserted one, we can describe its behavior as last in, first out. In short, we have the take-home message to understand the behavior of queue and stack. For queue, first in, first out, and for stack, last in, first out. Okay, let's first focus on queue and look at its major operations. In queue, the insertion operation is often referred to as in queue, which is identical to the pushback operation in array or linked list. The deletion operation is called dequeue, which is identical to the pop front operation in array or linked list. The operation that accesses the first data element is called front, which is the same as in array and linked list. A typical use of the queue data structure is to handle a series of random enqueue and dequeue operations. Here in the slide, we show the data content stored in the queue given a series of these operations. The first three operations are all enqueue operations, and we can see that the numbers are being inserted into the queue in order. The fourth operation is dequeue, and given the first in, first out behavior of queue, we will need to delete the data that is first inserted. And we can see that the corresponding number, 12, is deleted from the queue. The rest of the operations also follow this principle. There are many applications of the queue data structure in real life. One of the most intuitive applications is to model any simple queue. For example, we can model highway traffic using queue. We can treat the queue data structure as a highway that holds some vehicles. When a new vehicle arrives, we can use the enqueue operation to log its arrival. When an existing vehicle leaves, we can then use the dequeue operation to delete it from the queue. At different frequencies of dequeue and enqueue, we can model different levels of the traffic flow. Then, we can monitor whether the number of data elements stored in the queue will outnumber its capacity, in which case we have more vehicles on the highway than its maximum capacity and possibly lead to a traffic jam. Next, let's discuss the stack data structure. In stack, the insert operation is often referred to as push, which is identical to the pushback operation in array or linked list. The delete operation is called pop, which corresponds to the popback operation in array or linked list. The operation that accesses the last data element is called top, which corresponds to the back operation in array or linked list. Similar to queue, we can also perform a series of random push and pop operations on stack. In the toy example shown here, the first two operations are push operations, and we can insert 6 and 13 in order. For the third pop operation, we expect to delete the most recent data element according to the last in, first out behavior of stack. In this case, we remove 13 from the stack. The rest of operations also follow the last in, first out principle. In real life, the stack data structure's last in, first out behavior is used to keep track of the most recently processed object. One of its applications is to solve the symbol balancing problem, or making sure the matching of brackets and parentheses in the math expression. Note that the expression can contain different types of symbols that need to be matched. For example, it may contain parentheses, square brackets, and curly brackets at the same time. Consider the math expression that is colored red here. We need to decide whether its brackets are balanced. if we remove all the operators and operands and only keep the brackets, we can obtain a more succinct form of the expression. And we can easily verify that the symbols in cases 1 through 3 are imbalanced, while those in cases 4 and 5 are. Note that it could be challenging to make decisions using this approach when the expression gets longer. In this case, we will need an algorithm that works for arbitrarily long expressions. Let's look at the algorithm. The input of the algorithm is the original form of the math expression t, which contains symbols to be matched as well as the operators and the operands. The algorithm simply scans through the expression and uses a stack S to keep track of all the left-hand side symbols that have been examined. The algorithm handles the left-hand side symbols in lines 3 through 4. Once we see a right-hand side symbol, based on the matching rule, we need to match it with the most recently seen left-hand side symbol, which is expected to be stored in the stack S. If the match is successful, we can remove the left-hand side symbol from the stack. On the other hand, if anything goes wrong that prevents the matching, then we know the expression is imbalanced. Possible reasons for failed matching contain the matching of different types of symbols, such as matching a right parenthesis with the left bracket, or there exists no left-hand side symbol in the stack for us to match. The algorithm handles the right-left matching in lines 5 through 7. Note that if the symbol being examined does not correspond to symbols that need to be matched, for example, it corresponds to an operator or a part of an operand, then we do not need to do anything. In this case, we omit the else branch that considers this case. Finally, we need to check if the stack S becomes empty. Otherwise, it indicates that we have more left symbols than right symbols, which is another case of imbalance. We handle this case in line 8. If all things are checked, then we can report balance in line 9. Let's look at how this algorithm handles our toy examples. Note that we use the succinct form of the expression to simplify the demonstration. However, the algorithm should also work even if the expression contains operators and operands. In this slide, we have orange numbers and orange arrows. The orange numbers are the indexes of the symbols, and the orange arrows show in which line of the code the corresponding symbol is handled. For example, the first and the second symbols of the expression correspond to left-hand side symbols. By following the arrow that is labeled 1 and 2, we can see that they are handled in line 4 of the code. The third symbol is a right-hand side bracket, and we can match it with the most recently inserted left-hand side bracket. Once the matching is done, the left-hand side bracket is also removed from the stack. Following the arrow labeled by 3, we see that this right-hand side bracket is handled by line 6 of the code. After examining all symbols in the expression, we still have a non-empty stack. This is because we have pushed 2 left brackets but only popped 1. In this case, we report imbalance in line 8. Let's look at the second example. The first symbol is a left parenthesis and is pushed in the stack in line 4. The second symbol is a right parenthesis and is matched with the left parenthesis in line 6. The third symbol is also a right parenthesis. However, there exists no left symbol in the stack for us to match with it. In this case, we report imbalance in line 7. For the third example, we have the first 2 symbols pushed into the stack in line 4. The third symbol is a right bracket. However, the most recently inserted symbol in the stack is a left parenthesis, which cannot be matched with a right bracket. Therefore, the matching failed and we report imbalance in line 7. For the fourth example, the first 2 symbols are left symbols and they are both pushed into a stack in line 4. The third symbol is a right bracket, which can be matched with the left bracket in line 6. After the matching, the left bracket is removed from the stack and the next available left symbol becomes the left parenthesis. Then, we examine the fourth symbol and match the right parenthesis with the left parenthesis in the stack. The matching removes the left parenthesis from the stack and we end up with an empty stack. In this case, we report balance in line 9. Finally, for the last example, the first symbol is a left bracket and pushed to the stack in line 4. The second symbol is a right bracket and matched with the left bracket in the stack in line 6. After the matching, the left bracket is removed from the stack and the stack becomes empty. The third and the fourth symbols are processed in the same way. Once we have exhausted the expression and end up with an empty stack, we report balance in line 9. In summary, we have introduced the queue and the stack data structures in this video. The queue and the stack are derived from the array or the linked list and have a restricted set of operations. The restricted set of operations ensure the first in, first out behavior for queue and the last in, first out behavior for stack. Meanwhile, we have discussed potential real-life applications of traffic modeling and symbol balancing for queue and stack, respectively. In the next video, we will discuss the high-level idea for implementing the stack data structure. Thanks for watching and hope to see you next time.